me get started here. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to bless our work today. Help us to understand what we're covering about differential forms and how to calculate with them and everything. And we just thank you again, Lord, for your many blessings to us. In your name I pray, Lord Jesus. Amen. So, let's get into it. What is a differential form? All right. So I guess it's a little bit premature in some sense, because perhaps we should talk about vector fields, you know. But I'll just say this. That well, wait a minute, not on our end, my bad. On a manifold is where we are here, on M. So a vector field on M would just be a smooth assignment of a vector at each point. And you might well say, well, how would you define a smooth assignment of a vector? Well, that would just mean that if you know, so like sometimes we use the symbol this for vector fields on M. If X on F is smooth, given F a smooth function, all right? And by that, I in particular mean the mapping P maps to, like XP of F. So that's what we'd mean by a smooth vector field. It's an assignment of a derivation at each point, such that if you hit this derivation on a smooth function, then it defines a new function which is also smooth. You know, for example, and I will eventually get the differential forms here. If we had x equal to, you know, partial x1, let's say, on some coordinate chart, then, you know, if we feed that a smooth function, what do we get? Well, we get partial f partial x1, right, which is itself a smooth function. So certainly the coordinate derivations would be examples of vector fields, smooth vector fields, at least maybe not on the whole manifold, right? But if we localize this idea to, I should say, this is a vector field on M. So then if the domain of our chart is say V, I guess, then, you know, by a very similar argument, partial xi is a vector field on V. All right. Okay, great. And you can fairly easily see that if you have a vector field on V, you can express it how? If we had like V, a vector field, oh, bad letter. Oops, W, you know, a vector field, I'll make it a big W. A vector field on this chart domain, then you can pretty easily see that W could be written as what? Like the sum I equals 1 to n, well, I guess m for manifold dimension from m, of W acting on the ith coordinate chart, partial xi, right? And so now the vector field, right, its component, its components wouldn't be numbers. Now they would be honest to goodness component functions, right? Which is really what we talk about in, say, Calculus 3, vector fields, right? Yeah. So that's a vector field. I don't know, we would probably have more to say about vector fields this semester, but I'm going to focus the rest of today on differential forms, which perhaps we should call differential form fields, because they're really an assignment of a, a cotangent vector. It's like basically a smooth assignment of a cotangent vector at each point, like a one-form field. What would this say? A one-form field. And I'll put the field in parentheses because I'm not going to keep writing that. I'm just going to call it a one-form. But it would be something like P maps to, alpha sub P in the cotangent space to P of M, right? That would, but in order for it to be a one-form field, we'd like that to be a smooth assignment. How would you make that a smooth assignment? Well, actually, I don't really want to talk about that so much. That's kind of more the problem for next semester in the manifold theory course. There's where we'll care a little bit more about smoothness, okay? Here I'm going to be a little more nonchalant. But anyway, so basically we can write a one form as alpha is equal to, something like a sum over I equals 1 to m of alpha I dxi. Of course, this is really going to be only good for, v, a subset of m. It locally can be written like that in terms of a coordinate chart, right? And now, well, what are the alpha sub i's? How did we figured that out before, right? Like at a point, we got alpha sub I from what? From, what was it? I believe alpha sub I was equal to alpha on partial x sub I, right? At the point P, that's like alpha I of P would be that, right? And if you just let the P vary, I think you can see that the component functions here, right? Like alpha sub I should be alpha of partial xi. That's how we would, calculate the component functions for this one form field. So, yeah, but I think I'm getting ahead of myself actually, because what I do in the notes right here is something that's less troublesome. So let's just establish some terminology. I had the good sense in the notes to just talk about the basis first, and I see I'm making it more complicated here. I'm trying to talk about everything at once. But here's the notation. 0, if we have P maps, something that maps from P to R, is a 0 form, aka or function on M. If we have, for example, P maps to dxj. Now this is not an arbitrary one, right? This is a one form on M. And to be more fussy, it's a one form on a coordinate chart, because we might not be able to write the same dxi for the whole manifold, So dxi wedge dxj is 2 form on M. Let's see here.
Then what does that mean?
What is the what?
What does that mean that we're mapping P to dxi and dxj? Is that a union?
Well, I mean, to be fussy, I probably need a sub P here and a sub P here and a sub P here. Like a one form is a map from, it gives you a covector for each p. So the d sub p x upper j is a basis, forms the basis for the covectors. And technically speaking, these guys form a basis for what? I think in our previous notation it was lambda 2 of TPM, right?
So it's not single valued.
Oh, single, no, it's single valued. The functions, yeah.
Even the two form.
Yeah. I and j are fixed.
Yeah, but we're mapping on single vector b to.
P is not a vector, P is a point.
Oh, sorry, a point in manifold.
Yeah.
To both dxi and dxj.
Yeah, what I'm, let's see here, how can I say this? Maybe an example would be helpful, maybe. All right, so suppose my manifold is R2 Cartesian product with 3, okay? And I could look at the two form, alpha equal to, x d y wedge dz plus y dx wedge dy, maybe, I don't know. So like if I and then plus z, well, no, I'll just do that. Okay, fine. Maybe I should just rats. If I'm going to do this, it's a two-dimensional manifold. That's kind of boring in the sense that I really can't talk about. If I'm going to talk about a manifold on here, my coordinates on that are I should probably use x and y. So to be fussy, I mean, when I think about this manifold, I think about it in terms of an equation as z equals to 3, which if you're on the manifold with z equals to 3, well, that means that dz doesn't live there except at 0, I mean, I'm being heuristic here, but that's not wrong. So I really wouldn't, this is not quite what I want, I really should say something like alpha is, x, maybe xy plus 1 dx wedge dy, okay, something like that. There we go. That would be a two form on this manifold. You see, if I pick a different point, if I pick, for example, the origin, let me put the origin over here. If I pick the origin, in that sense, if I'm using x and y as coordinate charts, well, there I'd have alpha equal to what? See here, I'd have alpha equal to dx wedge dy. That's alpha of 0, 0. On the other hand, if I'm like, maybe here, if I'm alpha of, I don't know what that is. I guess if I'm drawing it that way, it's alpha of like minus 10 comma 2 or something, right? I go down here, I've got minus 10 times 2, minus 20 plus 1, minus 19 dx wedge dy, right? And so depending on what point I'm at, I'm assigning a different two form. So it's a two form field, technically. Right. So that's what I mean by this assignment. Now, admittedly, this is kind of dumb because I'm just talking about the basis, right? Like, what I really should write is something like, alpha is equal to a sum over I, alpha I dxi, that's a 1 form. A 2 form is something like beta is equal to the sum over, we could say I less than j, beta ij, dxi, wedge dxj. That's a 2 form, where the beta ij are functions, right? A p form, maybe let's talk about a q form. Well, I give a 3 form, and then a k form. I'll just go to the k form. Would something look like something like gamma, a sum over I1, I2, ik, and we could write it this way: 1 over k factorial, gamma I1, I2, ik, dx I1, wedge dx I2, wedge dx ik. I mean, that would be a k form. And here I'm letting the sum run from 1 to n, and then I divide by k factorial to, this would be under the assumption that the gamma I, the coefficients functions, gamma I sub 1 ik is completely anisymmetric, right? If you wanted to, you could write it as a sum over increasing indices, and then that would be a basis expansion. This is technically not a basis expansion because, if I switch the indices, I get minus what I started. So there's a linear dependence between between components that share the same set of indices. All right. And so I'm a little bit more explicit there on page 236. I'm like, okay, so a 1 form. So this is a 1 form. This is a 2 form, right? This is a k form. And to say that those are smooth, for our purposes, it suffices to say that the component functions of the forms are smooth, right? Like if you look at my example 1 discussion about vector fields, you could have, if you wanted to, you could have thought about it. Okay, so if I look at a coordinate system, I can expand the vector field like this. Well, if my vector field's given like this in a coordinate system, let's say that, maybe not even this, right? But if your vector field is given as like a sum over functions that are given here times the basis, well, if those functions are smooth, you could define that to mean a smooth vector field. That would then imply that if you hit it with a smooth function on it, the resulting thing is smooth, because you'd have a sum of partial derivatives of smooth functions, which of course is the product of smooth, smooth, smooth. It's smooth. It's everything smooth. All right. Oh, anyway, I said we're not going to talk about smooth in here, so let me shut up. All right, so just a recap of exterior algebra, because it's still here, right? And we have alpha, wedge beta, wedge gamma is alpha, wedge beta, wedge gamma. We have that alpha, wedge beta is equal to -1 to the pk beta wedge alpha. And we have that alpha, wedge a beta plus b gamma is equal to a alpha, wedge beta plus b alpha, wedge gamma. So here I'm assuming that alpha is a p form, beta is a k form, and gamma is an L form on the manifold. All right, so that means at each point of application there are corresponding, alpha is p form, beta is a q form, gamma is an L form on the manifold M. So we have proved these algebraic, or well, maybe prove is too strong a word. We have discussed we've discussed that the wedge product has these properties. I think we did prove this actually, but we've discussed the wedge product has these properties for a wedge product of dual vectors for a given vector space, right? So now we're talking about an assignment of such a wedge product of things at each point, a smooth assignment, right? But because the algebra holds at each point, it follows that we also have these algebraic rules for smooth one forms, right? So it's kind of like in Calc 3, you can prove the dot product of fixed vectors are commutative, right? It's still the case that the dot product of vector fields is commutative, right? The properties you prove for the cross product of vectors at a point, fixed vectors, those properties of the cross product are still true at the algebraic level for vector fields, right? Of course, there are new things. Once you have vector fields, you can start calculating the divergence or the curl, right? And the same thing goes here. Now that these are functions, we can introduce a calculus here as well. All right. Now, I guess just to make sure everybody's on the same page, let me look at R3, all right? And the, has exterior algebra, if you will. You could call it omega R3, right? And perhaps my notation is not quite, I don't know if I have a separate notation for differential form fields versus I don't know if I have a separate notation for the exterior algebra of form fields versus a fixed vector space. Like maybe there should be different symbols for those, but I hope that's not confusing. I don't know, maybe it is. But basically anything in the exterior algebra can be built by a linear combination of what? Something like you've got 1, you've got dx, dy, dz, dx wedge dy, dy wedge dz, dz wedge dx. These are not in any particular order. And then what else do you got? In terms of like basic wedge products of differentials, I think the last one is just dx wedge dy wedge dz, right? Those are all the sort of basic differential forms. And I'd like to say that those form a basis for the exterior algebra of differential forms in R3, but that's not quite true in the sense that the set of differential forms in R3 is not a vector space of, well, maybe it's a vector space, but it's not a finite dimensional vector space. See, because the components are functions. It is true, right, that you either have a function, you have alpha, which is something like adx plus bdy plus cdz, right? Or you've got something like beta is a, let's say, dy wedge dz plus b dz wedge dx plus c dx wedge dy, okay? And I would still like to use the notation we used before. I'd still like to say, well, fine, then there's gamma, which is something like g dx wedge dy wedge dz, okay? That's the so-called top form, the one I'm just writing. That's the only 3 form, but that's doesn't, g is a function, right? So technically we're not talking about a basis in the sense of linear algebra here, because now they're smooth functions. It is something called a module. We could say that, but let's focus here. So what I'd like to say is this, we'd still like to use the notation we introduced before. I'd still like to say that this is the work form of ABC, right? And I'd still like to say that this is the flux form of ABC, right? It's just now I'm thinking of A, B, C, F, and G as actually functions from R3 to R, right? Smooth functions. My marker doesn't work down here. What are you gonna do? Any questions? Okay. But that's, you know, as I think about R3, that's kind of it for what the, you know, smooth functions look like on R3. To me, those are the differential forms on R3 which I can write, okay? Now I have an example in the notes where I take a wedge product of some specific thing. It's not, I mean, I'm not going to write that on the board. It's not that interesting. Let's see here. Let's see here. This proposition might be important. Sometimes they are. If omega is a p-form on an n-dimensional space written in coordinate coframe dx1 through dxn at p, then the components of omega are given by evaluation on the coordinate frame. Okay, maybe I'll work this out here. Proposition 10.5.4. I think I was saying this before, but it's nice to have it written systematically. So omega is a p-form. All right, on M with coordinate, you know, x1, x2, da da da, xn, you know, on M. Now understand, I don't want to bury you in notation, but this is a local claim. I'm not saying that there's a global coordinate chart and that this holds for the whole deal. What I am saying is that at a specific point, or well, a specific neighborhood, this calculation holds, all right? Now omega being a p-form means that omega can be written as the sum, well, briefly it could be written like this, right? I, an element of the increasing indices of length p of omega I dxi, right? Now, in less than basically omega I is equal to omega of partial I. That's very schematically what the proposition is claiming. Okay, let me bring it to life in the proof. All right, let me not be vague. So specifically, to be a p-form means that we have omega is something like the sum over I1 less than I2 less than da, da, less than IP, ranging from 1 to n, right? And then you got your omega I1, I2, da da da, IP, dx I1, wedge dx I2, wedge da da da, wedge dx IP.
Why are the coordinates here in the book the x1 third the x1 instead of x1 third?
Oh. Well, that's the coframe. I said it's written in the coordinate coframe. So this right here is omega expanded in the coordinate coframe. So remember TPM is like partial xi, right? At the point P. Well, the coordinate coframe, TP star m, is dpxi. And we're doing that at each point in the domain of the chart for the differential form field. So let's see here. I think I had the good sense to, yeah, I had the good sense to write it in terms of the tensor. Yeah, let me stick with my notes because I'm setting myself up for combinatorial. Like if I do what I'm doing right now, I'm going to find myself back in the combinatorial mess we were in before. So I should just make use of what we've done before properly, which is to say that we can also write that as what? We can write that as omega equals to a sum over I1, I2, da 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 IP, right? Of 1 over, no. So sorry. Omega sub I1, I2, da 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 IP, dx I1 tensor, dx I2 tensor, tensor dx IP. See, I can do that because a P form is, first, it's a tensor, right? It's a, a type, I believe a type P0 tensor on TPM, and that's true for each point. My apologies that the point and the P might be conflated, but I hope they wouldn't because P is a number, whereas P is a point. Anyway, so if you want to calculate the components of a tensor, as we discussed, you do what? You let it act on, partial x, let's say j1, partial x j2, right? Partial x j p. And when we do that, we get what? We get the sum over the i's of your omega I1 through IP, and then we get what? We get like dx I1 of partial x j1, right? dx I2 of partial x j2, right? And down the line. But as we discussed last time, the differentials are the dual basis for the coordinate derivations. So those are all Kronecker deltas, right? Like this is Kronecker delta I1 J1, Kronecker delta I2 J2, Kronecker delta IP JP, and of course all we get is omega J1, J2, da da da, JP, which is the claim of the proposition. The claim of the proposition is just that the components of a differential form you can obtain by simply evaluating the differential form on the coordinate frame, provided you've written the differential form in the coordinate coframe. My apologies that I spent as long as I did on that proposition. It really, all we're saying is that what we did before still works, just in our new notation. Yeah, that's all that's really being said there. All right, so let's get to something more interesting. Yeah? So what's more interesting? Well, differentiation, all right? So the exterior derivative So let's see here. I'm going to erase this mess over here and start afresh. Now there's different definitions which you'll see given for the exterior derivative. Some people insist on defining the exterior derivative in a way which is manifestly geometric, in the sense that it is independent of a choice of coordinate systems. The definition I will give here is not that. The definition I give here is based in a particular choice of coordinates, and it's left to the reader to prove that this definition is independent of said choice of coordinates. The proof of that may or may not be in these notes. I do not remember. I will tell you this, the proof of that is not easy. Well, I mean, it's not impossible either. It's just basically a chain rule. It's just a chain rule is all it is. The chain rule and the fact that some of the things I'm writing here transform one way, and some of the things I'm writing here transform in the inverse way. So if we change coordinates, we still back to the same thing. It's always that. Anyway, here it is. Definition. If beta is k-form and x equals to x1, xn is chart, and beta is equal to a sum over the multi-index I of 1 over k factorial beta sub I dx upper I. All right? Then we define a k plus 1 form denoted by d beta to be the form as follows. In particular, d beta is equal to the sum over multi-index I of 1 over k factorial d beta sub I wedge dxi, where the differential of the coordinate functions is defined just as we did it in calculus 3, right? Where d beta I is the total differential. It's equal to the sum j equals 1 to n of partial beta I partial x upper j dxj. And if you'd like, I can be much more explicit. Let me do it. Here's what this looks like in much more explicit notation. This is the sum well. Well, I'm not sure I want to write it there. I'm not sure I believe it. All right. Ooh, I'm using a repeated index notation on multi-indices in the next page. Well, really? Well, okay. I guess at some point I got tired of trying to fit the sums in. Ooh. I think if I was to update these notes, I'd probably fix that. Because I'm trying to be less physicsy in some sense. I don't know if I'm succeeding or not, but all right, so let us just expand everything here a little bit. So what does this mean? Explicitly, that means that beta is the sum I1 dot 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 dot. It's a k form, so ik, that's the number of indices we got. You got your 1 over k factorial, and then we've got ourselves a beta sub I1 dot 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 ik. All right, dx I1 wedge dot 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 wedge dx ik. Okay, so d beta is equal to, so all d beta is really is you're just literally taking the exterior derivative of that and wedging it. That's all that really goes on. So I can write the formula for it just down here like so. It's the sum I1 dot 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 ik, also the sum j equals 1 to n, see that? 1 over k factorial. And so the differential of that is partial beta I1 dot 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 ik partial xj, and then that gives me a dxj wedge dxi1 wedge dot 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 wedge dxik. And so there you go. There's the formula for the exterior derivative in a non-multi-index notation. I can really explain what, like if you want me to explain how to exterior differentiate informally, it's simply this. You take the differential, you take the p form, and you take the total differential of the components of the p form wedged with what's there. So it's really just the natural extension of the total differential from Calc 3, where whenever you have two differentials, you have to have a wedge. Two or more. Like I can do some examples. So let's see here, like example 4. If I have alpha is like, you know, 3xy dz plus, you know, x squared dx plus, you know, y dy, there we go. And I want to calculate alpha, d alpha, of this one form. Here's how it goes. We take the we take the derivative of this, we wedge with dz. We take the differential of x squared, and we wedge with dx. We take the differential of y, and we wedge with dy. That is what this definition says. All right? So the total differential, you already know it. That's 3dx plus, oh, my bad. It's 3y dx plus 3x dy, right? Wedged with dz. And then you've got your 2x dx wedge dx. This is already 0. And this is 0. And this is what we have. So we've got 3y dx wedge dz plus 3x dy wedge dz. Now, I could also write this as minus, well, I could write it as 3x dy wedge dz minus 3y dz wedge dx plus 0 dx wedge dy. And from this, I can see, aha, well, that is the flux form of the vector field 3x minus 3y 0. And alpha was actually the work form of the vector field 3xy x squared and, oop, my bad. I gotta do right. Put things in order here. The first one was x squared. The y component was y. The z component was 3xy. So what gives? What's going on here? Do you know? How is this vector field related to that one? Not sure? Yeah. Fair enough. Let's see here. So I could write that as omega of the gradient of 1/3 x cubed plus 1/2 y squared, right, plus the vector field 0, 0, 3xy. Just saying you could do that. The kind of interesting thing is, of course, that would be what, you know, that would be 1/3, excuse me, that would be, you know, the x squared dx plus, you know, y dy, which I had up there, right? Plus this other one, right? You notice what happened under the exterior derivative. This piece here, right? The exterior derivative of that sent it to 0, right? So this is all from that piece. So I'll tell you what's going on here. Anyway, I'm just pointing out a pattern. That's not really my point. We can prove, in fact, that the exterior derivative of the work form of a vector field f is, in fact, the flux form of the curl of f. If you calculate the curl of this vector field right here, right? In fact, you know, you take the curl, when you take, let me give this thing a name. Let me call this vector here f apparently, right? That vector. When you take the curl of a gradient, what happens? Well, we know that the curl of a gradient is 0 from vector calculus, right? So like to double check my claim here, you can kind of ignore these pieces, you know, and just look at the curl of 0, 0, 3xy, which I'll remind you is like, you know, if you want this notation, this mnemonic, x hat, y hat, z hat, partial x, partial y, partial z, 0, 0, 3xy. That's my curl formula. So what do you get? Well, let's see here for the x hat. Partial, yeah, I get partial y of 3xy. And then for y hat, I get minus partial x of 3xy, right? And for z hat, I get 0. So what is that? Well, that's 3x minus 3y comma 0. Which is exactly what we have here, right? So that illustrates that that identity is true, but that's generally true. Let me do something easier. I mean, we'll prove properties of the exterior derivative here in just a second. The reason it's called an exterior derivative, do you know why? The reason it's called an exterior derivative is the exterior derivative of a p-form is no longer a p-form. Because you're introducing an extra differential, which is wedged with the others, you've gone from a p-form to a p+1 form. So in that sense, it's an exterior derivative. Like we could say this, generically speaking, D goes from like the p-forms on M to the p+1 forms on M. All right. Let me do it, before I get back into the general properties, let's just play around with R3 for a minute more here. Suppose you have an f, which is, a function of x, y, z, right? Smooth. Smooth function, right? If we take the exterior derivative of that, what do we get? df is partial f partial x dx, partial f partial y dy, plus partial f partial z dz. What is that in terms of the work form, the work flux form correspondence? Let me say the question a little bit more precisely. What is that in terms of the work form correspondence? That's the work form of what vector field? Omega sub what? Partial f partial x, right? Partial f partial y, partial f partial z, right? But what is that? In Calc 3 we have a name for, that's the gradient, right? So the exterior derivative of a function is the work form of the gradient. So there you go, that's another important relation. The exterior derivative of a work form is the curl of the flux form. The exterior derivative of a function is the work form of the gradient. All right, so this one notion of exterior differentiation, we see it's already encapsulating what? The gradient and the curl from Calculus 3. Now there's just one more differentiation in Calc 3 that we're super interested in, which would be the divergence, right? So what else do we have to differentiate here for, what if we differentiate the flux form? What would happen there? What's the flux form look like? The flux form of a generic function would be something like a times dy wedge dz plus, b times dz wedge dx plus c times dx wedge dy, right? That specifically is the flux form of ABC, right? Let me, okay, so is it okay if I use the phi in both ways? All right, great. Exterior differentiate this. What do you get? d phi is equal to dA wedge dy wedge dz plus dB wedge dz wedge dx plus dC wedge dx wedge dy. Now what is dA? It is partial a partial x dx plus partial a partial y dy plus partial a partial z dz wedge dy wedge dz. And for the next one, I'm only going to write down what matters, which is partial b partial y dy wedge dz wedge dx. And for the last term, the only one that matters is partial c partial z dz wedge dx wedge dy. Now, why do I just need to write those down? See what happens for this one? What do we say about the wedge product? If you have a repeat of a one form, any one form wedge itself is 0, right? So like this with that and this wedged with that wedged to 0, right? And I can, of course, I can commute them until they're up against each other. Anyway, the point is I've got a repeat of those differentials. Therefore, that wedges to 0. And the same happens for the b and the c. So all we have altogether is partial a, partial x, plus partial b, partial y, plus partial c, partial z. And notice that we can rewrite this as dx wedge dy wedge dz. See how the signs work? So this one, it's already dx. It's already x, y, z. This one, I have to move the x 2 spots. Bump, bump, bump. And this one, they have to move the z over here. I mean, there's other ways to see it, but the point is you can get from what we're given to that with an even number of transpositions of the differentials. And what is that? This, yeah, that's easier to recognize. That's the what? That's the divergence, right? Is that what you tell me? So, in other words, example 6, just to, put a ribbon on it, so to speak, the differential of the flux form of a vector field G is the divergence of the vector field G times dx wedge dy wedge dz. So the one concept, the one exterior derivative, simultaneously folds in all of our favorite derivatives from Calc 3. Setting aside, of course, like we do like the derivative of a path, don't we? We like that a lot. I'm not sure that's in here, so let me not try to oversell it. But it's got a lot, all right? So what are the properties of the exterior derivative? That's our question now. What are the properties of the exterior derivative? Is it linear? Yeah? Is it linear? Yes. What else could we say? So let's suppose we have alpha and beta, gamma, differential forms. And f function, yeah. I may not even need that, but certainly if we have the differential of, say, like alpha plus beta, then that is going to be the differential of alpha plus the differential of beta. That's going to be true. And in fact, more than that, if we have the differential of a constant times alpha, it's going to be a constant times the differential of alpha. Now, I think I've written what I just wrote there in one thing. I used an A and a B in the notes. But I'm expressing the linearity of the derivative in my number 1.
Does it satisfy the Leibniz?
That's where it's the interesting part. That's number 1. Number 2, what is the differential of alpha wedge beta? That's where it gets interesting. So supposing alpha is let's suppose alpha is a P form, okay? Now, here's the bad thing is I really should have used fine. I'm going to go back up here, Ernesto. I'm sorry. Alpha 1, alpha 2. Alpha 1, alpha 2, because, here, alpha 1, and I wanted alpha 1 and alpha 2 to have the same, in order to add them, they have to have the same degree, the same number of wedge products in them, right? But for 2, I don't want to assume alpha and beta have the same degree. Like alpha could be a P form.